Estamos gravando mais uma reunião. Não se espantem. Só um segundinho. Página 11.
Isso, a página 11, que tem as figuras 5. Pelo menos no artigo é a página 11. É isso, dá um zoom bem bom nessa aí. Nesta belíssima. Agora que eu vejo que eu tava ligado, né? Mas ok. Ele comeu uma faixa preta aí que tinha. Tudo bem na vida, né? Imagina uma faixa preta aí, tá?
Pronto, vamos lá. Deixa eu apresentar aqui para vocês.
E o outro, tu abre o outro.
Calma aí.
O Light Dark Matter.
Calma, tá ali, ó. O Light Dark Matter tá lá também. Vamos lá. Vocês estão vendo o David ou não?
Eu tô vendo ele muito bem.
Eu tô vendo bem. Em 2 gráficos.
So, good evening everyone, and today I will talk about a very interesting problem that the
Ó, David, todo mundo tá de máscara. Vai lá, tira sua máscara, porque senão eu não escuto, não.
Ok. Não fiz a barba, gente, então normalmente fica pouco. I will talk about a problem that the H0, the Rumble constants in the cosmology, local measuring, and very early universe measuring of H0 give to us different values. This is problematic because the whole cosmology depends of the H0. Why? Because the equation of the dynamics of the universe is that. So here has a key information, the Rumble parameter, all right? So a change in the Rumble parameter change very, or not so very, the dynamic of the universe, all right? So when you study very early universe, in this phase, only radiation is important, all right? In very early universe. So in the density energy of radiation, in a phase where electrons are not relativistic anymore, only neutrinos and photons are relativistic, we have a problem because studying the density energy of the radiation. Here we have the freedom of relativistic particles. This depends of the photon. Photon has two polarization states, so two freedom. And neutrinos are left-handed and antineutrinos are right-handed only. So G for neutrinos are 1. All right? We never saw a right-handed neutrino. Can be exist, but until this moment, only left-handed neutrinos exist in the nature. And we know electrons, tau, and muon. And each of these particles has a correspondence neutrino. So we have 3 families. So we say that the number of families of neutrino is 3. But this is weird because in 2016, and we find the community, the physicists find that any neutrino is different of 3. is bigger. So one possibility to solve this problem is imagining another family of neutrinos. Is one possibility. Another possibility is mimic the effect of this one extra neutrino, imagining that in the early universe exists some fraction of relativistic particle connected with dark matter. As we know, dark matter is cold. What is called dark matter for graduation, for undergrads? It's non-relativistic particle, all right? But if you imagine a distribution of velocity, it's possible to have some small fraction of particles in high velocity, but the biggest, the most particles are non-relativistic, but some small fraction can be relativistic. So we can imagine, and this paper that Fernando done up tell us how to mimic the effect of one extra neutrino.
Should I open this one now?
Yes, please. Mimic the effect of one extra neutrinos using a fraction of dark matter. And how we can produce this kind of dark matter? Please find out the page. There are not number here. Figure 1, page 2.
That's the one.
Yes. So let's imagine something. I think it's better in this way, right? Let's imagine that in the early universe, a mother particle K prime, we don't care about this particle, all right? This mother particle decays in a time moment. Tau moment. I don't know how to pronounce this Greek letter in English, but tau, all right?
It's tau.
And this particle decays in two other particles. Our loved dark matter and radiation or neutrino, all right? It's both possibilities are great. So if we imagine that this mother particle has a very high mass in comparison to the dark matter, we can imagine that a fraction of this particle, this dark matter particle, is relativistic, as I said before. So using, I will not show this equation. If you're interested, I can stay after and show how to do these calculations because the papers don't explain well. But we find that this fraction of dark matter here has a connection with the H0. For what reason? Show the other paper, please, for now. The trouble with here. Here, this paper is very, very interesting because the correlation, the delta N effective, what is delta N effective? N is free for the neutrinos, all right, plus something, all right? So this is delta N effective. So the Planck data, CMB plus lens, baryonic acoustic oscillations, all these data together form this region. We don't care about the others. This region here, all right? In this region, we have a direct correlation between H0, the Rambert constant, and the number of effective relativistic particle. And using that, we can correlate delta N effective, for example, H0, and the fraction of dark matter is relativistic before the matter radiation equality. So this paper gave to us this information. Give me age 0, and I told you delta N effective. And using this process, we can find this information. Give me F, M key prime over M key, and I will tell you the number effective. So using functions, we can create the following plot. F as a function of age 0. That is the other paper, please. So we see here that, as we know, age 0 is between 68, 73, and this region here is the lifetime of the mother particle, right? So imagine here a mother particle to 10 raised to 5 seconds of lifetime. And we are imagining that all these particles decays in the same moment for simplicity. Simplicity, yes. So in this region, this fraction have to be here in this space of parameters, all right? But for another time life is here, and here is more constrained, all right? So we can relate this and show that a dark matter can be change the value of age 0. But you can imagine it. Cold dark matter. If I change a lot the entropy of the universe, if I change a lot the number of the photons, I change what? Structure formation. I change a lot of well-behaved physicists. So we have to use all the cosmology to say that the F has to be very, very, very small to do not change this kind of structure formation and CMB and other things that we know the lambda CDM model is great to explain. So my work in this moment, I reproduce all this math, and my work is recreate this plot and the other plots of the paper, but using more recent data, because this data is 2016. I'm looking for more recent data to change this paper, this plot, all right? And add a more robust mathematics method to explain the expression of the paper, because there are some kind of confusion, and I try to explain step by step. So this is one of my works in this moment. I'm working on another one, but this is one of that, all right? Am I open to questions now?
Any questions?
Oh, any questions? I don't believe it. Everyone here understood everything? Iago, I have a question for you. No, I'm joking. So, I sent to Iago my calculations. I think it's.
Thank you.
All right.
Now, for this, let me try to explain to the undergrads. So, let me give you an idea. Let me try to explain what's going on. So the standard model of particle physics has 3 neutrinos. 3 neutrinos only. And these neutrinos are cousins of the known as leptons. A electron is a lepton. Muon is another lepton. And there's another one called tau. And they have cousins, which are called neutrinos. Electron neutrino, muon neutrino, and tau neutrino. These guys are also leptons, and they have many interactions that these ones have. So that's why we call them cousins. They're leptons. All right. So how many we have? 3. So this is standard model of particle physics. Particle physics only. And then cosmology says, okay, I don't care about the standard model of particle physics. I'm just to say, I want to know how many of these cousins exist in the early universe. We say, well, instead of 3, actually, I'm measuring, let's say, 3.5. What? Is either 3 or 4. You have 3 neutrinos or 4 neutrinos. You don't have 3.5. It makes no sense. How can you go from 3 in the standard model of particle physics to 3.5 in cosmology? Then there's one key important aspect. This number here is not precisely the same as the number of neutrino species. It's not the same. Here is the number of neutrinos. Here is the number of relativistic species. So this is not the same. This is just number of neutrinos. This is number of relativistic species in the early universe. However, there could be more species in the early universe which were relativistic and are not these ones. But this number is not just 3, 4, 5, 6, 7. There is some factor, temperature dependence here. That's why I can have 0.5, 0.7, 0.8. It's a function of temperature. So this thing is not either 1, 2, 3, 4. There's a function of temperature that I'm not explaining to you. That's why I can have 3.5, 3.4. And that goes to this paper there. You can just stay with the camera like this. I'm going to show this one. That's why this plot has numbers like 0.2. Look, this is an effective. I'll call it 3. Delta and effective is whatever is larger than 3. So delta and effective is 0.2, means that the ineffective is 3 plus 0.2. Delta and effective is 0.5, 0.6, then ineffective is 3 plus 0.6. But I measured, what we measured in 2016 was that the delta, the number of relativistic species changes according to H naught. H naught is the expansion rate of the universe today. How much the universe is expanding today. This is quantified by H naught. So what I'm saying is, if you change the number of relativistic species in the early universe, you change how fast the universe is expanding today. So if you change there in the early universe, you change it today. And that's quite amazing. Okay. And what we measured, so why this is relevant is because the CMB, the cosmic microwave background, says H naught should be 67, which is around here. And then when people go today and look at how fast the galaxy is expanding, they measure, wait, H naught is not 67, it's 72. But something which is like sacred, cosmic wave background, everybody knows about, even my grandma, she's on here. So everybody knows about, points to 67. And the precision we have is quite amazing. It's 67. But now you're saying that you look at the universe today and you quantify it to be 72. how can it be 72 if the CMB is telling me that's 67? And then people are trying to come up with ideas to explain why, when I measure today, galaxy expanding, I measure 72, but something from the universe, early universe, is telling me that should be 67. So something from the past is saying that today should be 67. I just extrapolate, saying 67. And if today you measure 72. So either you're measuring wrong now, or you somehow made a mistake with the CMB calculation. But it's very odd that you made a mistake with CMB calculation because many people arrive at the same conclusion. And the precision is really, really great. Okay, so the errors are really, really small. So someone has to come up with an idea to explain why CMB points to a value which is different than the one we measured today. That's called the H-naught trouble. Title of the paper, The Trouble with H-naught. And who wrote this paper? A Nobel Prize winner. The author of this paper is Rias. Rias is the guy who is one of the authors of the paper who discovered that the universe is expanding. It's accelerating and expanding. So it's not just expanding, it's expanding and faster and faster and faster. That's the guy who wrote that paper in 1999. Okay, so we have some of ideas. But then, if Hama says, but now let's include, like David said, a fourth neutrino. I am going to have now a David and neutrino David. But then this is not going to be 3.5, this is going to be 4. And if you go here to 4, which is equivalent to delta n effective equal 1, what you get? A value which is not consistent. Because it should be in this region. So you cannot simply add a fourth neutrino because you're not going to reproduce the data. You cannot add one. You have to add something which gives you 0.5, 0.2, 0.6, so it's not a fourth neutrino. And there are many ways how to solve this problem. One of them is saying, okay, I know that the universe, the dark matter exists in the universe for a very, very, very long time, since the very beginning. Maybe we don't know the nature of dark matter. Maybe the dark matter that was produced in the early universe was produced in a way, strange way. And when it was produced, maybe some of them were produced with a very high speed. So they were relativistic at that time. And then they will enter here as relativistic species. And that's the whole idea. So the calculation, I will not show you the calculations to do this, how we do this, but the idea is, if something was relativistic at that time, we'll increase the number of relativistic species to be larger than 3. And that's the idea of the paper, the other one. So we assume that some fraction of the dark matter that we know in the universe was produced with a very high speed. And if you do this, you can nicely reproduce this plot. So the idea of this paper is solving a crisis in cosmology. That's what they call it. It's not a crisis, but what they call it to sell the idea. Crisis in cosmology with particle physics. So it's where we combine cosmology with particle physics to solve a problem which is important for both. One is cosmology. Dark matter is also in cosmology. And it's also in particle physics, because if dark matter is a particle, the standard model that we know, the laws of nature we know, they are not complete. You need to add something else. So you need to add something else in cosmology and in particle physics at the same time. And that's the idea, to join the forces from cosmology and particle physics to solve a current problem in cosmology, which is how fast the universe is expanding. The universe is expanding faster than we expected. From C and D, we expected that H naught should be 67, but today is expanding at 72. And this number is this, H naught is 67 kilometers per second per megaparsec. So it's not very fast. So it's 67 kilometers per second is this. I think I guess my watch is not watching, so we don't know. My wife drives at that speed. But that's 1 per megaparsec. So the distance between galaxies is around 10 megaparsecs. So between one galaxy and the other, so it's very, very far. So I'm getting close to you at 67 kilometers per second. So I'm getting close to you, but you're also moving, right? So the whole universe is expanding. So I'm moving towards you at 67, and you're moving towards the wall at 67. Everybody's moving away at 67 kilometers per second. That's not very good. This speed is very small. At this scale, it's very small. It's very small. If you drive at the highway, it's that slow. Come on, get out of the way. At megaparsec scale, that's really, really small. But the number, instead of being 67 from CMB, we measured today to be 72. Okay? 72. And that's the idea. Any questions?
I still don't understand what NF really says.
Okay, so N affected the number of relativistic species or relativistic particles we had. So let's say that we are worried about the time where C and B was formed. The CMB, the cosmic microwave background, was formed quite some time ago, when the universe was still very cold. And at that time, roughly, but the only thing that matters actually, as David said, is that the matter radiation equality. Matter radiation equality. What is this? Is when the amount of matter in the universe is exactly the same to the amount of radiation. It's not amount, it's the energy density. The energy density of radiation and matter were the same value. That's what this is. So at that time, and then I asked, okay, did you have neutrinos? Yes, I have. How many? 3. Let's see if they were relativistic at that time. So if you count 1, 2, 3, yes, they were relativistic. Okay, 3. Who else was relativistic?
Photons.
Photons, yes, photons. But this thing, I'm not counting this equation, just counting neutrinos. Because this one, you have photons as well, but they will not count as this number here that I'm talking about. This number here, what other particles were relativistic at that time? So we have 3 neutrinos. Who else? Are there any light particles in the external model that could be relativistic at that time? No, they were not. So, okay, so the external model is saying that there are only 3. Cosmology is saying, asking, how many particles were relativistic in this period? And cosmology is telling us that was larger than 3. So because the external model tells you that there are only 3 particles, and cosmology is saying that's larger than 3. So this is the number of particles that were relativistic at that time. It's not just the number of particles. I'm telling you, there's a temperature dependence here. But this function that I'm not explaining to you. So you have to really do the calculations. There are some degrees of freedom. They wrote the equation as well. It's more complicated than the question. I'm just trying to simplify the idea.
It's because you can relate it if a particle is relativistic or not, depending on the temperature. If his mass is very large, more large than the temperature of the universe, you said that this particle is relativistic in that moment. So, depending of the temperature of the universe, some particles are relativistic and another not. For example, in the very, 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 very early universe, all particles were relativistic because the temperature is so high that we don't care about the mass of these particles.
Friends, give me think about it. 1.5 meters. And they, and they, okay, Aura has one in 80 centimeters, 180 centimeters. Okay. So he's clearly much heavier than her, right? So if I'm giving, let's say, I give an energy to Alvaro and Lorena at the same time, maybe Alvaro will be still non-relativistic because he's a little bit heavy. But Lorena will be boosting now with this energy. I'm giving the same energy to both, but she's relativistic and he cannot be relativistic. So, however, if I increase a lot the energy I give to both of them, Alvaro can now become relativistic. So, the energy that I give to these particles depend with time, change with time, because as the universe expands, it cools. So in the very early universe, it had a lot of energy. As the time goes on, this energy goes down and down and down and down. So in the very early universe, all particles were relativistic. Today, not many.
Today only photons.
Only photons.
Because
And
they
massless
were
and
faster, so they were.
Yeah, you had more energy around. So the more energy you have, the easier it is for me to make you relativistic.
What makes a particle relativistic is the velocity.
Right, so what we do here, we compare the mass and the temperature. So the temperature is the energy. So I'm giving an example. Your mass is fixed, right? You already have your mass, you already ate, right? So your mass won't change for an hour. Let's say your mass is 70 kilos, around that, right? 70 kilos. But then in the early universe, I'm telling you that the energy I had was, let's say, 10 to 10 kilos in energy. Well, I have to convert to energy. I'm making C speed velocity equal 1, right? Because this thing is not correct, the energy. The units is not correct. I'm just comparing. The energy I could give you is 10 to 10. The mass you have is 70. So if I throw all this energy at you, you're going to become a relativistic particle because my energy is much greater than your mass. So this represents this as kinetic energy, and this is mass mass. So have you seen the?
It's not kinetic. This is the whole energy.
Yeah, it's the whole energy that the universe is giving you. So let me write down like this. So you've seen this equation before. M2 C4 plus P2 C2. Have you seen this equation before? So this one is let's assume, just to make it simple, this one is the universe is giving you. This one is the one you already have. You have mass, so you have this one. But then, remember, when we are talking about non-relativistic particles, the momentum is 0, and we get the famous Einstein's equation, which is P equals mc squared. Because P is 0, you get just the equation, right? But however, if this particle is relativistic, what does it mean? It means that if this term is much larger than this one, you are a relativistic particle. So your momentum is much larger than your mass. But what is momentum? It's the energy I'm pushing.
So I need a very large mass and very large velocity.
You're going to have a very large mass and you're going to have a large velocity. But you don't have to have a large mass. Doesn't matter if you're heavy or light. If I give you enough energy, you're going to be relativistic anyways, as long as I have enough energy. But in the very early universe, I had enough energy. I would make you relativistic whether you want or not.
And the distribution.
Okay? So, what I'm saying, at that time, this time here, the temperature was not that high. I didn't have so large energies. So only these particles here, these three, supposedly they were relativistic. only these three. I didn't have much energy in this period. I didn't have much. Because if I had them, all of them would be just these three. But then the cosmology is saying, wait, but it's not at that time. It's not 3. It's 3.5. But as a particle physicist said, what? I don't have 3 or 4, not 3.5. Makes no sense. But, I need one more. But beta is telling me 1, 1, 1, 1. I cannot have 1. Delta and effective, one more. The number 1, I cannot have it. I cannot have 2, would be way up there. I can't have it. I have to have within these region here, which goes from 0.4, 0.6, 0.8, but no one.
So there's no new neutrino.
There is no new neutrino.
Not in the same that in this moment it's relativistic.
Right.
It can be an extra neutrino so massive that they are not relativistic in this moment, but it's another kind of neutrino, right?
I don't want to even go into this. But relativistic neutrinos, I cannot have just one more. It's not consistent with it. There's one very important message. So it's cosmology is telling to the particle physicists that you cannot have a neutrino, doesn't matter what your model, that's light enough to be relativistic at that time. Because it's here, I'm telling you, you cannot have it. But my model is supersymmetry, extra dimension, you cannot have it. Cosmology is saying that you cannot have it. So that's when it's really important to correlate cosmology with particle physics. So they are, depending on the topic you're working on, these fields merge. Cosmology and particle physics. Okay? And thus, what we call particle physics.
Soccer play in this moment.
I don't even know how he does. Okay, that's all. Bye, everyone. I hope you like it. Bye. Pronto.
Ele me deu assim, deu nem tempo de eu tava.